Hello folks, this is section 5-4. This is video number 2. So where I left off last time was I was talking about the multinomial distribution, and we were going to start working on this one example in detail. However, if you don't mind, I want to back up just a tiny bit here and make sure you read this multinomial distribution. It's similar to the binomial, but instead of only having two choices or two outcomes, you can have any number of outcomes. The requirements are right here. Make sure you read that, but I wanted to point out this one right here. The trials are independent. So just like in the binomial distribution situation, we always say that the trials have to be independent. Another consequence of that requirement is that if you are selecting when you're selecting things, like you're drawing a coin, or excuse me, you're drawing a survey, or you're doing something of that sort, there must be replacement. There must be replacement if you want these trials to be independent. Now, does that make sense? If you're drawing a card from a deck of cards, if you don't put the card back in there, then the next time you draw a card, the probabilities are going to change. So they're not independent. However, there is a concept here. It says, again, note that the multinomial distribution can be used even though replacement is not done. So if you don't replace the card, provided that the sample is small in comparison with the population. So we had that example before about talking about people that went to the doctor, very small sample. We didn't replace them, but the sample size compared to the entire population is so small. What we basically do is we say, well, it's close enough for government work. Okay, so I told you last time, I want you to go ahead and look at these examples yourself, and I urge you very, very strongly write them out in detail. So now we're going to talk about selecting the colored balls. So we're going to talk about this in detail. He's got it written down here, of course, but let's see if we can figure this out. Let's really do a good job. Annotate our comments. I'm going to give you an example of how I do it, and I'm hoping that you'll do it the same way. All right, so these are my lecture notes for section 5-4. I think I mentioned this last time. This is just the reminder to myself that this is the combination formula. N choose R. This is the formula. We talked about this before, and I also mentioned that we use a special notation when we're talking about binomial coefficient, and it's also a little bit of a special notation for the multinomial distribution. It's the same concept, but instead of saying N choose R, we say N choose X. X is the number of successes. Okay, so the multinomial distribution. Okay, so in my notes here, obviously I've written out in a fair amount of detail the definition. I recommend you do that. I recommend that you annotate it as much as you need to make it clear to you. Now, some people will need more annotations, some people will need less. It doesn't matter. Just do what it takes for you. Okay, so we got this, the x sub 1, x sub 2, x sub k. Those are the subscripts. It's just a way of identifying them. We could, instead of writing down the subscript, we could have written down, well, X sub white balls, X sub blue balls, X sub red balls, or whatever. But that's just too cumbersome. What we normally do is we use numbers, okay? So that's how we normally do it. Okay, so it's very important that you understand that the x sub 1, x sub 2, all the way up to x sub k, that's the number of successes. That's the number of times that we are interested in each of these events occurring. Okay, so we'll see here in just a minute what this really means. It's the number of successes. How many times do we get E1, for example? How many times do we get E2? Then N is the summation. We add up all of the x sub i's. So the way most math books will do this is they'll say x sub I, and then I goes from 1 to k. You see how this notation is? There's the I, there's the I. That's just the way we normally do it. And when you add up all of the possibilities, you know, how many times do you get a success in x sub 1, how many times you get a success in event number 2, and so forth. It all adds up to get you the n. And then the summation of all of the probabilities is equal to 1. That's just one of the rules of probability. Okay, so here we go. Example 527. We're selecting the colored balls. The box contains blah, blah, blah. I'll let you read that. 5 balls are selected. Find the probability. Now, this is the key thing. It's find the probability that out of those five that you picked, 2 of them are white, 2 of them are red, and 1 is blue. Okay, what is the probability of getting that exact outcome, so to speak? Okay, so here's how I do it. I think it makes more sense if you write it out in a little more detail. Here's my little dictionary. The events E1, E2, E3. The event for E1 is the white ball is selected. The event for E2, what is it? What does that mean? That means a red ball is selected, and so forth. The number of times, the x sub 1, it's asking you right up here, what's the probability that 2 are white, 2 are red? Well, that's just right here, and then 1 is blue. So I'm writing it out in detail to make it more clear to me and hopefully to you. So now, what are the probabilities? The probability sub 1 is 4 over 10. That's the probability of picking a white ball. Every time you pick a white ball, the probability of that happening is 4 over 10 because there's 4 white balls and there's 10 balls in general. The next one, P2, same idea. It's a probability that you pick one red. 3 out of 10 are red, and so forth. Okay? So this big X here is the probability of getting this exact sequence of what we're looking for. What's the probability of getting exactly 2 white, exactly 2 red, exactly 1 blue? Okay, so add those guys up. That gives you the n. That's 5 in this case because we are picking 5 balls. So you add those guys up and that gives you what your n is. Okay. All right, well, here's the formula. It looks like a horrible formula, but it honestly, it's not that bad. N factorial, that's just the 5 factorial. X sub 1, that's the number of successes of event number 1, which is right here. So that's 2. E sub 2 is the red selected, so X sub 2, we're asking what's the probability of getting 2 of the reds. So all of that's just being plugged into the formula. So it's 2 factorial times 2 factorial times 1 factorial. And then here, these are the probabilities of each of those guys. So probability 1, that's the probability of event number 1 happening. That has to happen X sub 1 times. You pick a, gosh, I'm sorry, I forgot what it was, whites. You pick a white, and you do 2 of those. On the reds, you pick a red. So each time you do that, they're independent events. You have to, you multiply the probabilities. Okay, so that's where this portion comes in. This portion comes here. Before, when we only had 2 different categories, we called that a binomial coefficient. Well, we can't call it a binomial coefficient now because obviously this isn't a binomial. This isn't binomial. There's more than 2 guys down here. So I don't know. I don't think there's any particular term for that. That's just the coefficient. That's just the guy right up here. That's how many ways can you get this. All right. And I guess that's all I have to say about it. You crank this out and you come up with an answer. You have a handy dandy calculator. You don't need a fancy calculator, just a little $5 calculator will do it. You crank this out and you get 0.1296. That's the probability of getting that exact set of balls. Okay, so that's 0.1296 is approximately 13%. So there's a 13% chance of getting the balls that we desired. Okay, so now, many times, this is what I'm showing you right here in this section is a very good idea. I commend this to your attention. My advice is don't just do the problem and then say, okay, I got that problem, I got it right, I looked in the back of the book, I got the right answer, and then just go back to watching the Kardashians or playing beer pong. It's very important to write things out in detail and kind of explore the different concepts. Now, one of the concepts that the author mentioned was that binomial is merely an example of multinomial. Okay, well, let's see if that's true. Let's discuss that. And so here's my discussion. Binomial is an example of multinomial. There are 2 events, success or failure. For example, heads or tails. Okay, so if I had that, if I said there's two events, if I said, well, all I have is, instead of having three events of a, where's that at? Here it is. Instead of having the three events of picking a white, picking a red, picking a blue, let's suppose I had the events of heads or tails. Is this formula that we have up here, is it the same? Does it give us the same answer, I guess? So this is example 516 from page 277. We did it back then. We did it using the binomial distribution. Let's see if we can get the same answer here. So we toss the coin 3 times, find the probability of 2 heads. So event 1 is a head, event 2 is a tail, x sub 1 is 2, x sub 2 is 1. The probability of this guy here is 1/2. Probability of this guy here is 1/2. Each one of those successes, you know, the probability of a success, the probability of getting a head is 1/2. Okay, my big X here, the big X without a subscript, that's the outcome of 2 heads and 1 tail when I flip the coin 3 times. This symbol here means therefore. It's a mathematical symbol. So here's the formula for multinomial. I'm going to plug everything in just exactly like I did before. And I get 3/8, which is exactly the same answer as we obtained using the binomial distribution. And you can kind of see here why that's working. You know, it's x sub 1 times x sub 2. Well, if x sub 1 is 2 factorial, this guy right here has got to be n minus x sub 1, okay? And if you look back on the formulas, that's exactly what we had before. Let me see if I can get back to that. Okay, right here at the beginning. See, it was n, the coefficients that you use for the binomial distribution, this n subtract x, and then it's x factorial. So this would be like the number of heads, and this is the number of tails. So if you flip it 3 times, you get 2 heads. N minus 2, that's 3 minus 2, is 1 tail. Okay, that right here is exactly the same as what we had a moment ago. Let me bounce back down to that. Okay, so it's n choose r or n choose x, you know, 3 take away 2. You know, 2 successes for the heads means there's 3 minus 2 successes for the tail. So compare this formula, or this number here, with the formula we had before, and you'll see it's exactly the same. Okay, so you know, this is telling us that, yeah, the author is correct. The binomial distribution is indeed a special case of the multinomial distribution. And I make a little note here, n minus x sub 1, that's x sub 2, since there are only 2 events, heads or tails. Now this symbol right here, that's very common in math. People, when they write math stuff, a little box, sometimes they'll put coloring inside, sometimes they'll just leave it as an empty box. That means, okay, I'm done. This is exactly what I was intending to do. I'm totally done. It's kind of like writing the end at the end of a book, at the end of a story. Okay, so those are my handwritten notes for multinomial, and we'll come back here in a little bit to the Poisson distribution. That's the end of this tape.